Hey everyone! Today, we're going to build a complete web API using ASP.NET Core 10. We'll start from scratch using Visual Studio Create endpoints, connect a simple database, and test everything with Swagger UI. Whether you're new to ASP.NET Core or upgrading from .NET 8 or 9, this tutorial will get you ready for 2025 projects. Let's jump in. In this video, we're going to create a simple book review app. This tutorial is completely beginner-friendly, so even if it's your first time working with web APIs, don't worry. We'll go step by step together. Alright, let's get started. Inside Visual Studio, click on Create a new project. In the search bar, type Web API. You'll see multiple templates. Make sure to pick the one that supports Linux and Windows. For the project name, let's call it Book Review App. Of course, you can name it whatever you want if you're creating your own version. Totally up to you. Once that's done, click Next, choose your .NET version. We'll use .NET 10 in this tutorial. Before we click Create, let's double-check a few important settings. First, make sure OpenAPI support is enabled. This is what's going to give us Swagger, which lets us test and explore our API directly in the browser. Next, make sure the Use Controllers option is checked. This will generate a controller folder and a default weather forecast controller, so we can start building endpoints right away. Finally, under Authentication Type, select None. We'll add authentication later in the series. Once all of that looks good, go ahead and click Create. Alright, now let's clean up the default files that come with the Web API template. First, open the Controllers folder and delete the file named Weather Forecast Controller. We won't be using that in our book review app. You can also delete the Weather Forecast model file. Microsoft adds these by default, just to demonstrate how an API project works, but we're going to build everything from scratch, so we don't need them. Now, let's take a quick look at the Program.cs file. This is the entry point of our application. You can think of Program.cs as the brain of your API project. It's where we configure everything, from database connections to dependency injection, authentication, and middleware. In simple terms, middleware are the building blocks that process every HTTP request. Things like authentication, logging, exception handling, and routing all pass through here. We'll be coming back to this file throughout the tutorial as we start wiring up our database, adding identity for users, and registering our services. For now, it's good to understand that this file controls the overall pipeline of our application. Now let's start building the structure of our book review app. Inside our project, let's create a new folder and name it Models. Models are really important. They represent the data structure of your application. You can think of a model as a blueprint for your database table. Each property in the model becomes a column in the database. Inside the Models folder, let's create a new class and name it Book.cs. In this class, we'll add a few simple properties. The ID property will act as our primary key. Title is the name of the book, and release date will store when the book was published. Later, we'll connect this model to a database using Entity Framework. But for now, this gives us a clean starting point for our data layer. Now that we've created our book model, let's also add another model to represent the author. Inside the same Models folder, right-click and add a new class named Author.cs. Just like before, this model will represent another table in our database, this time for the authors who wrote the books. Let's add a few simple properties. Here will be our primary key. Name stores the author's full name, and bio will hold a short description or background information about the author. Models like book and author will help us structure our data and later define relationships between them. For example, one author can write many books. Next, let's add one more model to our project, this time for country. Inside the Models folder, right-click and add a new class named Country.cs. This model will represent the countries where our authors are from or where books were published. Let's keep it simple and give it two properties. The ID is our unique identifier, and name will store the country's name, like France, USA, or Japan. Later, we'll connect this model with our author model, so each author can have an associated country. This helps us organize our data and relationships clearly. Now let's add one more model, this time for category. Every book belongs to a specific category, like fiction, science, or biography. Inside the Models folder, right-click and create a new class named Category CS. Just like our other models, we'll keep it simple with two properties. The ID will be the unique identifier for each category, and name will store the name of the category itself. Later on, we'll connect this model to our book class so that each book can have one category, and that will help us organize our API data much more cleanly. All right, now it's time to add one of the most important parts of our app, the review model. Inside the Models folder, right-click and create a new class named Review.cs. This model will represent the reviews that users leave for books. Let's start by adding an ID property. This will act as our primary key. A primary key is a special column in a database that uniquely identifies each record. For example, if we have 100 reviews, the primary key makes sure each review can be found individually. No duplicates, no confusion. Here's what each one does. ID uniquely identifies each review, our primary key. Title, a short headline for the review. Text, the full review content written by the user. Review date, when the review was posted. Reviewer, the name of the person who wrote it. Book, this links the review to the specific book being reviewed. Later, when we connect our database using Entity Framework, this book property will create a relationship between the review table and the book table, showing which review belongs to which book. Now, let's add one more model, this time for the reviewer. Inside the Models folder, right-click and create a new class named Reviewer.cs. This model will represent the users who actually write reviews for books. Let's add three simple properties. The ID will be our primary key, just like in other models. It uniquely identifies each reviewer in the database. The first name and last name properties store the reviewer's name. Later on, we'll connect this model to our review class so that every review will be linked to the reviewer who wrote it. That relationship will help us track who posted each review and make our data more organized and meaningful. Now, let's go back to our book model and set up a relationship between books and reviews. A single book can have many reviews, but each review belongs to only one book. That's what we call a one-to-many relationship. To represent that, we'll add a collection of reviews inside our book class. Let's open the book model and add this property. This line tells our application that a book can contain multiple reviews. When we connect our models to a database later with Entity Framework, this relationship will automatically create a foreign key in the reviews table that points back to the book it belongs to. In simple terms, think of it like this. One book has many reviews, but each review has only one book. This kind of relationship is very common in database design, and it helps us keep our data structured and easy to query later. Now, let's do the same thing for our country model. Each country can have multiple authors who come from that country. And this is another example of a one-to-many relationship. One country has many authors. To represent that in our model, let's open Country Model and add a new collection property. This property tells Entity Framework that one country can be linked to many authors. Just like before, when we create the database, EF will automatically set up a foreign key inside the author table that points back to the country it belongs to. So now, our data model is starting to take shape. Now, let's go back to our reviewer model and add another relationship. A single reviewer can write many reviews, but each review belongs to only one reviewer. That's another classic one-to-many relationship. To represent that, let's open the reviewer model and add a collection of reviews. This tells our application, and later, Entity Framework, that each reviewer can be linked to multiple reviews. When we build the database, EF Core will automatically create a foreign key inside the review table that connects each review to its reviewer. In simple terms, one reviewer has many reviews. One review has one reviewer. This makes it easy to query all the reviews written by a specific person or find out who posted a particular review later in the app. Now, let's move over to our author model and set up a link between authors and countries. We know that every author comes from a specific country, so this relationship is a many-to-one. Many authors can belong to one country. To represent that, let's open author class and add a new property. This tells our application that each author has one country associated with them. When we connect this to a database, Entity Framework will automatically create a foreign key inside the author table that points to the country this author belongs to. A foreign key is simply a reference from one table to another. In this case, from the author table back to the country table. So now our data model is starting to make more sense. Countries have many authors, and each author belongs to exactly one country. Now let's do the same thing for our review model. We already know that one reviewer can write many reviews, but each review should belong to only one reviewer. So let's open Review Model and add a new property for the reviewer. Now let's create one more model to connect our books and categories together. A book can belong to many categories, and each category can include many books. That's what we call a many-to-many relationship. To represent that, inside the Models folder, let's add a new class named Book Category. Here's what's happening. ID is the primary key for this table. Category ID will act as a link to the category table. The book property references which book belongs to this entry, and the category property points to the specific category. So each record in this table will connect one book with one category, and together they form a many-to-many relationship between the two tables. This design keeps your database organized and makes it super easy to query all categories for a given book, or all books under a certain category. Now, let's create one more model, this time to connect our books and authors together. A single book can be written by many authors, and one author can write many books. So this is another many-to-many relationship. Inside the Models folder, let's add a new class named Book Author. Here's what each part does. Book ID links to the book table. Author ID links to the author table. The book property represents the book itself, and the author property represents the author who wrote it. Together, each record in this table connects one specific author with one specific book. And that's how Entity Framework understands the many-to-many relationship between them. So later, when we create our database, we'll be able to easily find all authors for a given book, or all books written by a particular author. Now that we've created our book author and book category models, let's go back to our book class and connect everything together. Remember, one book can have many authors and also belong to many categories. To represent those relationships, let's open the book file and add two new collection properties. The first property, Book Authors, connects this book to all of its authors through the Book Author Bridge table. The second one, Book Categories, links this book to all of its categories through the Book Category model. When we build the database, Entity Framework will automatically understand that these are many-to-many relationships, and it will handle all the foreign keys and linking tables for us. In other words, a book can have many authors and belong to many categories. Each author and category can also be shared across different books. This structure gives us a flexible and realistic way to represent books and their relationships in our API. Let's do the same thing inside our author model. Remember, one author can write many books, and one book can have many authors. So this is a many-to-many relationship. Now, let's finish setting up our relationships by updating the category model. All right. Now that we've finished setting up all of our models and relationships, it's time to connect our application to a real database. For this tutorial, we'll be using Microsoft SQL Server Management Studio, also known as SSMS. Inside SSMS, open the Object Explorer panel on the left, right-click on the Databases folder, and choose New Database. In the dialog box that appears, let's give our database a name. We'll call it Book Review App. You can use any name you want, but make sure it matches the name you'll use later inside your code. Once you've typed the name, click OK, and SQL Server will create your new database instantly. You should now see Book Review App appear under the Databases list, and that's where all of our tables and relationships will be created later when we connect it to our Web API using Entity Framework Core. Now that we've created our database in SQL Server, let's connect it to Visual Studio so we can manage it directly from our development environment. Now, head over to Visual Studio, open the SQL Server Object Explorer window. You can find it under the View menu if it's not already visible. In the Object Explorer, click the Add SQL Server button. In the panel that appears on the right, paste the server name you copied earlier from SSMS. Then, select the authentication method. For most setups, you can use Windows Authentication, and from the drop-down, select the database we just created, which is Book Review App. Finally, click Connect, and Visual Studio will link directly to your SQL Server database. You'll now see your book review app database appear inside Visual Studio. And from here, we'll be able to create tables, run queries, and connect it to our Web API. Now that our SQL Server database is ready, let's connect it to our Web API using a connection string. A connection string is basically a short line of text that tells our application where the database is and how to connect to it. Inside Visual Studio, open the file named appsettings.json. This is where we store our configuration settings. Let's add a new section at the top called Connection Strings, and inside it, let's define one for our book review app. Once that's added, save the file. This connection string will later be used by Entity Framework Core to connect our models and automatically generate the database tables. Now that we've added our connection string, it's time to install Entity Framework Core, which will help us connect our models to the database. Entity Framework, or EF Core, is Microsoft's ORM. That stands for Object Relational Mapper. It basically lets us interact with the database using C# classes instead of writing SQL manually. To install it, go to Tools, NuGet Package Manager, manage NuGet Packages for solution. In the Browse tab, search for Entity Framework Core SQL Server. This package allows Entity Framework to talk directly with SQL Server. Once that's done, install one more package, Entity Framework Core Design. The design package gives us extra tools for running migrations and managing our database structure from Visual Studio. After both packages are installed, you'll notice that new references have been added under your project's Dependencies folder. And that means Entity Framework Core is now ready to use in our Web API. Now that we've installed Entity Framework Core, it's time to create the class that will actually connect our code to the database. Inside our project, let's create a new folder and name it Data. This folder will contain everything related to our data access, including the database context class that talks directly to SQL Server. Inside the Data folder, let's add a new class and name it Data Context. This class will inherit from DB Context, which is the base class in Entity Framework used to represent a database session. What we're doing here is defining our DB sets. Each DB set represents a table in our database. So for example, books will become a table called Books, authors will become Authors, and so on for all of our models. In other words, we're telling Entity Framework, these are all the tables we want you to create and manage for us. This Data Context class is the bridge that connects our C# models to the SQL Server database we created earlier. Now that we've defined all our DB sets, let's talk quickly about something important inside Entity Framework called onModel Creating. Inside our data context, we can override a method called onModel Creating. This method allows us to customize how Entity Framework builds our tables and relationships. For example, EF Core automatically detects relationships based on the navigation properties we defined in our models, like the one-to-many link between book and review, or the many-to-many links between book and author. But sometimes we need to fine-tune that configuration manually. In this example, we're telling Entity Framework that both book author and book category tables should use a composite key, combining two columns, the book ID and the author, or category ID. We use this because these are linking tables in many-to-many relationships. Even though EF Core can sometimes detect this automatically, it's always a good habit to define composite keys manually when you're working with join tables. So think of onModel Creating as the place where you can precisely control how your database gets built. Now that we've created our data context and added our connection string, it's time to connect everything together inside our program file. This is the step where we tell our application to use Entity Framework Core and point it to the database we created earlier. Let's open the program file. Inside the service configuration section, right after Builder Services Add Controllers, let's add the following code. What we're doing here is registering our data context. The Use SQL Server part tells Entity Framework that we're using Microsoft SQL Server as our database provider. Now that our database is connected, let's add some initial data to it. This process is called seeding. Inside our project, let's create a new class and name it seed.cs. The seed class will be responsible for populating our database with some starting data. Things like sample books, authors, categories, and reviews. I've already written a full seed script for you. You can find it on my GitHub repository. The link is in the description below. Go ahead and copy everything from that file and paste it inside your seed.cs class. This will give us a ready-to-use setup that automatically fills the database the first time we run the app. Once you've added the class, we need to tell our application to inject it into the dependency container so we can call it during startup. Let's open the program file again, and inside the service registration section, add a transient. Add transient means that every time the application requests a seed instance, it will create a new one, which is perfect for setup or initialization logic. Later, we'll call this class inside the program file so that it can populate our database automatically when the API starts. And just like that, our seeding system is ready to go. Now that we've connected our project to the database, the next step is to set up our migrations. Inside Visual Studio, open the Package Manager console, and we're going to run the command add migration initial create. This command tells Entity Framework to generate all the database tables based on our models. Sometimes you might run into a few errors during this step, and that's totally normal. Don't worry, we'll go through them together and fix everything step by step. Awesome! Once the command finishes running, you'll notice a new folder has been created automatically inside your project. It's called Migrations. This folder contains your very first migration, named Initial Create. Inside it, you'll find all the C# code that Entity Framework generated based on your models. This is what EF Core will use to build your database tables. So basically, each migration represents a snapshot of your data model at a specific point in time. Now that our migration has been created successfully, let's update our database. Inside the Package Manager console, type the command Update Database and press Enter. This command will take all the migration code that Entity Framework generated and apply it directly to our SQL Server database, creating all the tables and relationships we defined in our models. Once it's done, our database will be fully in sync with our project. Entity Framework just created the Book Review App database and automatically generated all the tables based on our models, including books, authors, reviews, categories, and more. Now, if we open SQL Server Management Studio or the SQL Server Object Explorer in Visual Studio, we can actually see all those tables inside our database. That's it. Our database is now fully synchronized with our application. Now that we've set up our seed class and registered it inside the program file, all we need to do to populate the database is simply run the application. When the app starts, the seed class will automatically execute and insert all of our sample data into the database. Once it's finished running, you can head back into SQL Server Management Studio and open your Book Review App database. Inside the Tables folder, you'll see that Entity Framework has created all the tables for our models: books, authors, categories, reviews, and more. If you right-click on any table and choose Select Top 1000 Rows, you'll see that the data is already there. Books, authors, categories, and reviews have all been successfully inserted. So with just one run of the application, we now have a fully populated SQL Server database ready to be used in our API. Now that our database is ready and filled with data, it's time to organize how our application will interact with that data. In this part, we're going to implement something called the repository pattern. The repository pattern is a design pattern that helps us separate our business logic from our data access logic. In simple terms, instead of having our controllers directly talk to the database, we create repositories that handle all the database operations for us. This makes our code cleaner, easier to test, and more maintainable in the long run. Think of a repository as a middleman. It sits between your API controllers and your data context, making sure all database access is handled in one place. To get started, let's organize our project structure. Inside your project, right-click and create a new folder named Interfaces. This folder will contain all the interface definitions for our repositories. Then create another folder named Repository. This one will hold the actual implementations of those interfaces. With these two folders in place, we're ready to start building repositories for our models, like books, authors, reviews, and so on, each responsible for handling its own data operations. Now that we've set up our Interfaces folder, let's start by creating our first interface. This one will handle all operations related to books. Inside the Interfaces folder, right-click and add a new file named iBookRepository.cs. In C#, interfaces are like contracts. They define what methods or operations a class must implement, but they don't contain any code themselves. Think of it as a list of promises. Any class that implements this interface must provide the actual logic for the methods we define here. Let's start simple. Inside our book repository interface, we'll add a method that returns a collection of books from the database. Now that we've defined our interface, let's go ahead and create the actual implementation for it. Inside the repository folder, right-click and add a new class named Book Repository. This class will implement the iBook repository interface we just created. In C#, when a class implements an interface, it must provide the actual logic for every method that the interface defines. Let's start by making our class implement the interface. Let's break down what's happening here. We're injecting our data context into the repository using a constructor. That allows this class to communicate directly with our SQL database through Entity Framework. The method getBooks returns a collection of all books from the database, ordered by their ID. The repository acts as the data access layer. It focuses only on reading and writing data, keeping our controllers clean and easy to maintain. Now that our repository is ready, it's time to create our first API controller, the one that will handle all book-related requests. Inside the Controllers folder, right-click and add a new class named Books Controller. At the top of the class, we'll add two important attributes. These two attributes tell ASP.NET Core that this class is an API controller and that it will handle HTTP requests for the route API books. The root attribute defines the URL pattern, and APT controller enables helpful API features like automatic model validation and cleaner responses. Now, inside our controller, let's create a constructor and inject our iBook repository. By injecting the repository, our controller can now access all the data operations defined in the book repository. This is where dependency injection really shines. We don't have to create the repository manually. ASP.NET Core automatically provides it for us, thanks to the registration we'll set up inside the program file. With this setup, our controller is now ready to handle requests and return book data directly from the database. Now that our controller is connected to the repository, let's add our first HTTP GET endpoint to return all the books in the database. This is what allows clients, like Postman, Swagger, or even front-end apps, to request data from our API. Inside the Books controller, let's add the following method. Here's what's happening. HTTP GET tells ASP.NET Core that this method will handle GET requests. Produces response type specifies that the method returns a 200 OK response containing a list of book objects. We call book repository getBooks to fetch the data from our database. Finally, we return the data wrapped in an OK response. This is the simplest form of an API endpoint. It receives a request, gets data through the repository, and sends it back to the client in JSON format. Once this is done, run the app and go to the Swagger UI. You'll now see a new route called Get API Books. Try executing it, and you'll see your list of books coming straight from the database. Now, before we run our API, there's one very important step we don't want to forget, and that's adding dependency injection for our repository. Remember how we injected the iBook repository into our Books controller constructor? A sp.NET core doesn't automatically know how to create an instance of that repository. We have to tell it how to do that. And we do it by registering our repository inside the program file. And right under where we registered the DB context, add the following line. Here's what this line means. AddScoped tells ASP. Netcore to create one instance of the repository per web request. The first type, iBook repository, is the interface we depend on. The second type, book repository, is the class that implements it. So, whenever the controller asks for an iBook repository, ASP.NET Core automatically injects an instance of book repository. This is what we call dependency injection. It's one of the most powerful features in ASP.NET Core because it helps keep our code clean, modular, and testable. Once that's added, save the file and run the app again. Your Books controller will now receive its repository automatically, and your API endpoints will start working perfectly. Now that we've got our basic getBooks method working, let's add a few more detailed endpoints to make our book repository more powerful and complete. These methods will allow us to get a specific book by its ID, get a book by its title, retrieve a book's rating, and check if a specific book exists in the database. Let's open our iBook repository interface and add the following methods. Here's what each one does. GetBook returns a single book that matches a specific ID. GetBook with string title returns a book using its title. GetBook rating with book ID retrieves the average rating for that book. We'll implement this logic soon. Book exists. Checks if a book exists in the database, returning true or false. By adding these to the interface, we're defining the contract for our repository, which means that every class implementing this interface must include these methods and their logic. In the next step, we'll move over to the book repository class and implement these methods to make them actually work with the database. Now that we've added our method definitions inside the interface, it's time to implement them in the book repository class. Let's start with the getBook method. This method will return a single book from the database where the book's ID matches the parameter we pass in. Inside our book repository file, let's add the following implementation. Here's what's happening. We're using LINK to filter our books table and find the book where the ID equals the value we received from the request. The first or default method will return the first match, or null if no book with that ID exists. This is a clean and efficient way to query data using Entity Framework Core. Now, let's go ahead and finish implementing the rest of our methods in the repository. First, for getting a book by title, we'll do almost the same thing as before. Filter by the title and return the first match. Next, let's add a method to check if a book exists by ID. And finally, a method to get a book's rating. Here, we'll use the reviews to calculate the average rating for a specific book. Now that our repository is ready, Let's talk about something really important before we start building our API endpoints. DTO, which stands for Data Transfer Objects. Anytime we build an API endpoint, it's a good practice not to return our database models directly. Instead, we use DTO. Simple objects that define exactly what data we want to send or receive through our API. This helps us in 3 ways. It protects our internal database structure. Clients only see the fields we choose to expose. It keeps our responses lightweight and clean, without unnecessary data. It gives us flexibility. We can change the database model later without breaking the API contract with our clients. So, inside our project, let's create a new folder called DTO. This folder will contain all the data transfer objects for our app. Things like Book DTO, Author DTO, Review DTO, and so on. In the next step, we'll create our first DTO for books and start using it in our controller responses. Now let's add another HTTP GET endpoint inside our book controller, this time to retrieve a single book by its ID. We'll define a new action called getBook, which takes the book ID as a parameter. We'll also specify our response types, a 200 response that returns a single book object if everything goes well, and a 400 response if something goes wrong. For example, if the book doesn't exist. This gives our API a clean and predictable way to fetch individual books by their unique identifiers. Now, let's add another endpoint that will return the rating of a specific book. We'll define a new HTTP GET route called bookid/rating. This action will first check if the book exists, and if it does, it will fetch and return the rating value. We'll specify a 200 response type of decimal, since the rating might be something like 4.5, and a 400 response type if the book ID isn't valid. This endpoint is useful when we want to display the average rating of a book without fetching all the review details. All right, now it's time to test our API. Let's go ahead and run the application. This will start our web API locally and host it on a development server. Once it's running, we can open the and send a GET request to our endpoint at API Books to make sure everything is working correctly. If everything is set up properly, we should see our list of books returned in JSON format. That means our controller, repository, and database connection are all working together perfectly. Now, let's test our next endpoint, getting a single book by its ID. In the browser, I'll change the request URL to API Books 1 and keep the method as GET. Then I'll hit Send. If the book with ID 1 exists, we should see all its details displayed as a JSON object, including the title, author, and any other properties defined in our model. This confirms that our root parameter is working correctly and that our controller can handle individual book lookups by ID. And that's it for today's video. We've successfully built and tested our book review API, from setting up the models and controllers all the way to running it and testing our endpoints in Postman. If you found this helpful, make sure to like the video, subscribe to the channel, and turn on notifications so you don't miss the next part, where we'll start adding more endpoints and connect this API to a real front end. Thanks for watching, and see you in the next one. Now, let's create a new interface named iCategory Repository. This interface will handle all the logic related to categories, including getting all categories, retrieving a specific category by ID, fetching books by category, and checking if a category exists in the database. Later, we'll implement this interface in a new repository class to connect it directly to our database using Entity Framework. Now that our interface is ready, let's create the implementation class, Category Repository. This class will handle all database operations related to categories. Inside the constructor, we inject our data context so we can access the database through Entity Framework. Then, we implement each method. GetAllCategories returns a list of all categories. GetCategory retrieves a single category by its ID. GetBooksByCategory gets all books that belong to a specific category. And finally, CategoryExists checks if a category exists before performing any operations. With this repository in place, our API can now manage categories just like it does with books. Now let's create our category controller to expose our new endpoints. This controller will allow us to fetch all categories, get a specific category by its ID, and list all the books that belong to a particular category. We start by injecting our iCategory repository into the controller so it can access all the category-related data from the database. Then we define 3 get endpoints. The first one, API categories, returns all the categories. The second one, API categories ID, returns a single category. And the third one, API categories ID books, returns all the books linked to that category. With this controller in place, our API can now manage both books and categories seamlessly. And we can test all these endpoints directly from Postman. Now let's create a category DTO class. DTO stands for Data Transfer Object, and it helps us control exactly what data we send back to the client. In this case, our category DTO will only expose 2 properties, the ID and the name, since that's all we need when listing or displaying categories. This keeps our API responses clean and focused without exposing unnecessary details from our database models. Now, let's update our category controller to use our new category DTO. Instead of returning the full category model, which could include extra data and relationships, we'll map each category to a simpler DTO that only includes the ID and name. This keeps our API responses clean and focused, while also protecting our internal database structure. Later on, we can even automate this mapping using a library like AutoMapper. But for now, we'll do it manually with a simple select statement. Now, let's create a new interface called iCountry Repository. This interface will handle all database operations related to countries and their authors. We'll start with a method to get all countries and another to get a specific country by its ID. Then we'll add a method to find a country based on a given author and one more to list all authors from a specific country. Finally, We'll include a simple Boolean method called country exists, which will help us validate country IDs before running other operations. This structure will make it easy to manage the relationship between countries and authors inside our API. Now let's implement our iCountry repository interface inside a new class called Country Repository. Just like before, we inject our data context through the constructor so we can access the database using Entity Framework. Then, we implement each method. getAllCountries retrieves all the countries from our database. getCountry gets a specific country by its ID. getCountryByAuthor finds the country an author belongs to. getAuthors from country lists all the authors associated with a given country. And finally, country exists checks if a country record exists before we do anything else. With this repository done, we now have all the logic we need to manage countries and their authors in our application. Now that our country repository is ready, let's expose it through a new controller called Countries Controller. Just like our previous controllers, we start by injecting the iCountry repository into the constructor. Then we add 4 endpoints. The first one, API countries, returns all the countries. The second one, API countries ID, returns a specific country by its ID. The third endpoint, API countries author ID, allows us to find the country that an author belongs to. And finally, API countries ID authors returns all the authors associated with a given country. With this controller, our API can now manage countries and link them to their authors, giving us a clean and powerful structure for the next parts of our book review app. Now, let's create a country DTO class. Just like our category DTO, this data transfer object will define exactly what information we expose from our country model. In this case, we only need 2 fields, the ID and the name. This makes our responses much cleaner and prevents us from accidentally exposing complex relationships or sensitive data. Using DTOs like this is a best practice in any modern API because it keeps our internal data structure separate from what the client sees. Now that our country DTO is ready, let's refactor our countries controller to use it. Instead of returning the full country model, which could include extra details and relationships, we'll map each country to a simple DTO that only includes the ID and name. We use a link select statement to project our data from the model to the DTO before sending it back in the response. This keeps our API responses lightweight, secure, and perfectly structured for client-side applications. In the next steps, we can do the same for authors and books, keeping our entire API consistent and clean. Now let's go back to our program file to register all our dependencies. We'll add each of our repositories to the dependency injection container: the book repository, the category repository, and the country repository. This allows ASP.NET Core to automatically create and inject these services wherever we need them, like in our controllers, without us having to manually instantiate anything. Finally, we make sure our data context is connected to the SQL Server database, and we're ready to start testing all of our new endpoints. Now that our book repository is working, let's move on and create another repository, this time for authors. Inside the Interfaces folder, let's add a new interface and name it iAuthor Repository. Just like before, our interface will define all the methods that any author repository must implement. Let's start by adding the following methods. Now that we've defined our iAuthor repository interface, let's create the actual implementation class that will handle all author-related data. Inside the repository folder, right-click and add a new class named authorrepository.cs. This class will implement the iAuthor repository interface and use our data context to interact with the database. Now that our author repository is ready, we need to tell our application how to use it. Just like we did with our book repository, we'll use dependency injection to register the iAuthor repository in our Program.cs file. Let's open the program file, and right below the Add Scoped line for books, add this new one. Once that's done, let's create a new controller to handle all author-related API endpoints. Inside the Controllers folder, right-click and add a new class named Authors Controller. At the top of the class, add these attributes. Then inject our repository using the constructor. Now our controller is ready to communicate with the database through the author repository. In the next step, we'll start adding our HTTP GET endpoints to fetch authors of a book, and books by a specific author. Now that our authors controller is working, let's create a data transfer object for authors, the author DTO. Just like we did with book DTO and category DTO, this DTO will define what data we want to send to the client instead of returning our full database model. Inside the DTO folder, right-click and add a new class named Author DTO. Let's add the following properties. Now that we've finished setting up our repositories for books and authors, let's move on to the next important part of our app, reviews. Reviews are a key part of our book review app, and to handle them properly, we'll create a new interface named iReview Repository. Inside the Interfaces folder, right-click and add a new file called iReview Repository. Just like before, this interface will define all the methods our repository must implement to manage reviews in the database. Now that our iReview repository interface is ready, let's go ahead and create its implementation class. Now that our review repository is fully implemented, let's register it inside the program file so our controllers can use it through dependency injection. Once that's done, we're ready to create our reviews controller. Now that our reviews controller is ready, let's create a DTO for reviews, called Review DTO. This will help us control what data gets exposed through our API responses, and it keeps the structure clean and lightweight. Now that we've created our Review DTO, let's update our reviews controller to use it instead of returning full review models. Now that our reviews are working perfectly, let's move on and create a repository for reviewers. Reviewers are the users who actually write the reviews, so we need a way to manage and retrieve them from our database. Now that we've created our iReviewer repository interface, let's go ahead and create its implementation. This class will handle all reviewer-related database operations and implement the methods we defined in the interface. Now that our reviewer repository is implemented, let's register it inside our Program.cs file and create the reviewer's controller to expose these methods as API endpoints. Inside the program file, let's add one more line under our other repositories. Now that we've finished setting up all our repositories, DTOs and controllers, it's finally time to test our API. Go ahead and run the application by clicking the Run button. Each one should return clean and data, formatted according to the DTOs we created. You now have a fully functional backend API that's clean, modular, and ready for future features like authentication or front-end integration. Now that we've finished setting up our GET endpoints, it's time to move into the next important part of our API, updating data. In this part, we'll focus on the update methods, starting with our categories. To begin, let's open our iCategory repository interface and add a new method called updateCategory. This method will allow us to update an existing category record inside the database. Let's add the following line of code. Now that we've added our new updateCategory method to the interface, it's time to implement it inside our category repository class. Now that we've implemented the updateCategory method inside our repository, let's expose it through our API using an HTTP put endpoint. Before we move on to testing everything in Postman, let's fix a small but very common mistake in our controller. Alright, now that we've fixed our parameter name, let's jump back into Postman and test our GET endpoint again. I'll send a GET request to, let's hit send. And perfect. We get a 200 OK response with our JSON result showing the category details. We're ready to move on and test the put endpoint to update our data. In the URL bar, I'll enter. Then I'll go down to the Body tab, select Raw, and choose this from the drop-down on the right. Now, let's add our new category object. Once that's ready, I'll click Send. If everything's set up correctly, we should get a 204 response. That means our category has been successfully added to the database. We can confirm it by switching back to a GET request and calling all categories. Now that we've finished updating the category endpoints, let's move on and add the same functionality for our country entity. We'll start by adding an update country method inside our iCountry repository interface. Now that we've added the update country method to our interface, let's go ahead and implement it inside our country repository. Open the country repository file. Just like we did for categories, we're going to use Entity Framework's update method to mark an entity as modified and then call save to commit changes to the database. Our update country method is ready inside the repository. Let's connect it to our API by creating a put endpoint inside the country's controller. Open the country's controller file and add the code. Now that our category endpoints can read data, let's add the ability to create new categories. Inside our iCategory repository interface, we'll add a new method called createCategory, which will take a category object as a parameter and return a Boolean value indicating whether the operation was successful. We'll also add a save method that we can reuse later for other operations like updating or deleting categories. These methods will let us handle the post requests in our API and add new categories directly to the database. Now let's implement the methods we just added to our category repository. Inside the repository, we create a new method called createCategory, which takes a category object as input, adds it to our entity framework core context, and then calls the save method. The save method simply commits all pending changes to the database and returns true if at least one record was affected. This structure gives us a clean, reusable way to handle database operations across all our repositories. And now our API is ready to accept new categories through a post request. Now let's add our post endpoint inside the category controller. This endpoint will allow us to create new categories by sending a JSON object in the body of the request. We'll first check if the incoming data is valid, and then verify that a category with the same name doesn't already exist in the database. If everything looks good, we map the DTO to our category model and call createCategory from our repository to save it to the database. Once it's created, we return a success message. In Postman, we'll be able to test this endpoint by sending a post request to API categories with the category name in JSON format. Alright, now it's time to test our new post endpoint inside Postman. I'll open Postman and create a new request. Set the method to post, and in the URL, I'll type our endpoint. Next, I'll go to the Body tab, select Raw, and choose JSON as the format. Inside the text box, I'll write a simple JSON object like this. Then I'll click Send. If everything works correctly, we should get a 200 OK response and a message saying, "Category successfully created." And just like that, we've added a new category to our database. Our post endpoint is working perfectly. Now that we've added our new category, let's test it by displaying all categories using our get endpoint. Select the get method and call the category's endpoint. Once I hit send, we can see the full list of categories, and there it is, the new category we just created. Everything is working perfectly. Our post method successfully adds data, and our get request confirms it in the database. That's all for this video. In the next one, we'll work on the HTTP delete method, so we can remove categories directly from our API. If you're enjoying this series, don't forget to like, subscribe, and turn on notifications so you don't miss the next episode. In this final video of the series, we're going to add the delete method to our API so we can remove categories directly from the database. Let's start by updating our iCategory repository interface. Here, we'll add a new method called deleteCategory, which takes a category object as a parameter and returns a Boolean value to indicate whether the deletion was successful. We'll use this method later in our controller to handle HTTP delete requests and remove categories safely from our system. Now that our interface is ready, let's implement the new method inside our category repository. We'll create a method called deleteCategory, which takes a category object as a parameter. Inside, we simply call context removeCategory to mark the entity for deletion, and then call our save method to commit the changes to the database. This keeps our repository pattern consistent. Every operation, whether it's create, update, or delete, goes through the same save process. With this done, our repository is fully equipped to handle deletions, and we can move on to wiring up the delete endpoint in our controller. Now let's finish this series by adding our delete endpoint. Inside the category controller, we'll create a new method called deleteCategory and decorate it with the HTTP delete attribute. This will handle all delete requests to API categories ID. First, we check if the category exists in the database. If not, we return a not found message. If it does exist, we retrieve the category, call our repository's delete category method, and then return a 204 no content response to confirm the deletion. Once this is done, we can test it in Postman by sending a delete request to our endpoint. And just like that, the category is permanently removed from the database. Now, let's test our delete endpoint using Postman. I'll open Postman, create a new request, and change the method to delete. Then I'll enter the URL, where 2 is the ID of the category I want to remove. Once I hit send, we get a 204 no content response. That means our category was successfully deleted from the database. To confirm, I'll switch back to our GET request and run it again. The deleted category no longer appears in the list. Everything is working perfectly. And that's it. With this, we've completed our operations for the category entity: create, read, update, and delete, using ASP.NET Core 10, Entity Framework Core, and Clean Architecture Principles. If you enjoyed this series, make sure to like, subscribe, and stay tuned for the next part, where we'll extend this API even further.